Let me begin by thanking Bhushan, Prashant, Dr. Manu Lopez, and CBS for inviting me to give this lecture. Its title is The Saga of the Indian Science Olympiad. What are the Science Olympiads? Briefly speaking, the Science Olympiads are like the Olympics, but it is for academics and not sports. It is held every year and not every 4 years, and it is held in different subjects: physics, chemistry, biology, junior science, maths, etc. And it is important to note that it is always at the pre-college level. Once you enter college, you do not qualify to become a team member of the Science Olympiads. So what were we? We were not team members. We were like leaders or mentors or national coordinators or whatever of the Science Olympiad efforts. Let me throw some light on that. This is basically going to be a popular lecture. It is going to be a personal lecture, and it's going to be a lecture for the pioneering period of the Science Olympiads. That is not the later part, that is the recent part, but the early struggling period. That's what it will be. Popular, personal, and pioneering period. So let me begin with the personal. The prevailing notions on Indian science, when I got back from the United States, and say I was traveling on a train or basically sitting in a canteen and having tea with people, were the following. And let me tell you what they are. Okay, government institutions are ineffective and hopelessly quagmired in bureaucracy. Voluntary science bodies exist to criticize these government institutions and grab newspaper headlines. And we have perhaps the world's largest manpower in science that occupies some average position in world science. Okay, this was the prevailing notion in the 80s and early 90s, and it bothered some of us, and it bothers a lot of us, I think, who are very concerned about Indian science. Okay, so what I'm going to tell you is a short story. It's a true story. It may sound like a fairy tale, but it's a true story. And it's a story that will, in a very modest way, it will debunk these myths. Okay. So let me begin with the personal. It was 1990. I was in the US as a visiting professor, assistant professor, and I was visiting the Rensselaer Polytechnic Institute as a speaker. And in the audience was Robert Resnick. We all know who he is. Resnick and Halliday have written the most famous book and the most popular book in India at the preschool, pre-college level on physics. And his third edition had come out. So I sought an audience with him. He said, I'm very busy, but do come in. And he autographed and gave me this book. It says, to Vijay Singh, best wishes. And it is 9/21/90. But it is not the book that is important. Sitting in that hall, in that room with him, were some of the best science or physics teachers of the United States. Larry Kirkpatrick, who became the president of the IAPT, A.P. French, who was a professor at MIT, Arthur Eisencraft, and others. And they all urged me at that point that I should involve India into the Science Olympiads. Why were they doing it? Because they had gathered in RPI, in that Institute of Resnick's, to train students for the Science Olympiads. That was July, for the Science Olympiads that was to be held in a so-called enemy country. It was supposed to be held in Cuba that year. And after that, they kept badgering me, in fact. I wrote to them, they wrote to me, and this is something from 1994, a letter from A.P. French, room number 101 of MIT, okay, where he says that Indian participation in the International Physics Olympiad must happen. That's what he wanted to do that. Okay, I tried, of course. I mean, it's not as though I was not trying, but the IIT was not interested. The NCRT, as I mentioned, my first slide, it was hopelessly quagmired in bureaucracy. It didn't happen there. But it happened in an interesting way, and I will get to it in a minute. Okay. But before that, I took one problem from one of the selection tests in the East European countries, okay, and I gave this problem as, and I managed to turn it around a little bit, change it a little bit, to be honest with you, and gave it in the joint entrance exam of 1995. That is problem number 3. It carried a full 10 marks. And what was interesting about the problem, it's 10 marks here, it is 1995, and it's interesting because it was the first time that you had a problem of refractive index which was varying continuously. It was not as though it's fixed refractive index problem. So you had to set up a differential equation. Okay, the refractive index was changing as you went up the height. The height is given by y. Okay. So my intention is not to tell you how to solve this problem, but to tell you that this problem was like a testing the waters, as they say. How good are we, our students, as far as the Olympiad is concerned? And here was the problem in the IIT in a pressure cooker situation, and I was willing to bet that they would ignore this problem and do the others so that they qualify. But I was wrong. In those days, not lakhs of students, but only 70 or 80,000 students would take the IIT, out of which 16,000 took them in the Kanpur zone, and fully 10 students got this right. And I was very pleased. And I thought perhaps we have some hope in the Olympiads with this kind of a performance in a pressure cooker situation. So my hope was built up. Let me continue. Okay, this is 1998. Okay. I became the editor of the Bulletin of the Indian Association of Physics Teachers in 1997. And in 1998, while I was in Kanpur, okay, here in Bombay, a few gentlemen got together, a few people got together and launched the Olympiad movement. That was basically the IAPT, okay, my body with which I was associated, and the DAE. Okay. So it is the first instance I think of in science as a good public-private partnership which became successful. And as soon as this is what I advocated immediately in the bulletin as the editor, that the Physics Olympiad is being launched. This is the acid test, okay, and several of us believe that our young aspirants shall perform ably in the International Physics Olympiad. So this was our hope. So we welcomed it. The Olympiads were happening. How did this happen? There was a teacher association which had a vast coverage over India, the IAPT. There was a government institution willing to put its money where its mouth is, the DAE, and a memorandum of understanding was signed between IAPT, DAE, and the intermediary for the DAE was the Homi Bhabha Center for Science Education, and this signed it. Okay. I got involved in it right from the beginning, and I've had a ringside seat to the Olympiad since that time. So in a sense, I am a sutradhar of this whole Olympiad movement, Science Olympiad. So let me tell you something. Now let me come to the Olympiads to some extent. So let me take one example. I can't describe all the Olympiads: physics, chemistry, biology, junior science, and astronomy. So I'll take an example, say, of the chemistry Olympiad. It was started by East European countries. Who started it? There were 3 countries which began it. Czechoslovakia hosted it, 68. Okay, and now I will show you how the Olympiad evolved. In 74, the first non-European country, Eastern Bloc country, participated, Sweden and Yugoslavia. This is all chemistry. Okay, 1980, the first time it was hosted outside the Eastern Bloc. Some of us who know history know that there was a Cold War going on between the Eastern Bloc and the Western Bloc. Okay, and it was hosted in Austria. In 1984, the USA, the so-called top enemy country for the Eastern Bloc, entered the game. Okay, they participated. So the Olympiads are something which are very good, which bring us together. They don't divide. Okay, and a new subject was introduced along with the standard ones, biochemistry. 1989, the People's Republic of China entered. Okay, so it was China coming in. Okay, 1992, the USA actually hosted their chemistry Olympiad, and a new subject, another subject was introduced, environmental chemistry. Okay. What about India? Our first participation was in 1998, and it was in physics, and it was in Iceland. And let me continue. 1999 chemistry, 2000 biology. Earlier, and I have to correct myself, 89 mathematics had started participating. Okay, and we hosted the mathematics Olympiad in 96, the chemistry Olympiad in 2001, the astronomy Olympiad in 2006, the biology in 2008, the Asian physics, also the Asian physics has its own Olympiad run by the IAPT, the Indian Association of Physics Teachers, in 2012, junior science 2013, and finally physics in 2015. What is the road to the Science Olympiads? I will show you this rather dense slide, but I will not go into the details. There is a 5-stage process, as you can see, 1, 2, 3, 4, 5. I do not expect you to remember all the acronyms, but let me stress here the first stage, in which about 40,000 students appear in physics, in chemistry, a lesser number in biology and astronomy, and in junior science. Okay. And this is the early period. The cost was not 1,000 rupees or 2,000. It was just 50 rupees per participant. And this happened because the IAPT, Indian Association of Physics Teachers, is a thoroughly voluntary body. Okay. It is spread all over India, and all its work is done by voluntary teachers, voluntarily by teachers. They don't charge money for it. Okay. And we have, there is a widespread, I mean, we have centers even in Arunachal Pradesh. In Andaman, we had a center. Okay. Even in those days I'm talking about, we had a center in on the remote corner of Himachal Pradesh. If a student requested us to waive the fee, the 50, that would also be done. That decision would be taken, and that would be done. So there was a very egalitarian and inclusive approach, and it took off immediately. After 40,000 students are selected in each subject, some 300 are given another exam by the Homi Bhabha Center for Science Education. By the way, I have to tell you 3 things. There were 3 players here, actually two, but the memorandum of understanding was signed by Professor Chidambaram on one side, from the DA side, Professor R.M. Dharkar from the IAPT side, and Professor Arvind Kumar from HVCSE, which was the nodal center. From 300, you come to 35, and from 35, this is the OCSC, or the training camp, or the selection and training camp. Then you take 5 students in physics, 4 in biology, and 4 in chemistry, about 6 in astronomy, and so on and so forth. Okay, and then they go to an international location where another 5 students come from their own countries. So if there are some 80 countries, you have 400 students. Each team is accompanied by 2 leaders, and there's a vast conglomerate of very young, a lot of young energy in this place, and a lot of friendship and a lot of competition. The host country does something wonderful. They put the best thing they have on display, because they know that these students, these young students, are going to be the future ambassadors of their country. Science ambassadors. Okay. So let me describe a problem or two. Okay, this was in Italy. This is an experimental problem. Okay, it's in physics, but I will describe a couple of biology problems and chemistry. Okay. And it is basically a pendulum which is tied over here. Okay, and it has got a thread. You see a threaded rod. As you change the threaded rod, you change the moment of inertia of the rod. Okay, as you change the length of that rod, you change something called the moment of inertia, which is nothing but the distribution of mass about this point. Okay. And therefore, you look for the oscillations, and the oscillation time period will change. Now, there are 2 things about this. There's a catch in this experiment, which the students have to realize, which I will come to in a minute. Okay. First, the most difficult thing was there were these nuts. I mean, sorry, these things that there was something called a rounded nut over here. Okay. There is something called an Allen nut. There are all kinds of screws that the students has to use. Okay. And there was all kinds of, there was a round nut in the end. And our students were sadly wanting in this. Okay. Because what happens in our culture, and even now, is that a parent will agree to pay his ward, his daughter or son, 100 rupees so he can get a flat fixed, instead of telling him, open up the toolbox and fix that puncture or that flat in your tire. So we don't actually tell them to do that. We just give them 100 rupees and say, go and change it and come back and study. Sit on your desk and study. So the culture of experimentation is just not there. Okay. So our students were wanting, and I'm very indebted to one of the two leaders who went there, Professor Darkar, and I was the other leader who explained all the niceties of this. So the IFPT teachers, college teachers, have played a very important role in the experimental part. Okay, they know all this, and we from IITs who sit in our ivory towers don't know this. Okay. So what was the catch? The catch was the following. As you change the distribution of mass about this point, okay, the position, the stable position goes from the center, it has a bifurcation. There are two other positions. Okay. So let me come here and show it to you. So it may oscillate like this, but it will also oscillate like this or like this, depending on the moment of inertia. So there's something called, in physics, it is called symmetry breaking, or in chemistry, it's like the ammonia molecule. Okay, and therefore that was not told to the students, that they had to discover. And a lot of students also floundered there, they didn't know what was going on. Okay, so it was that kind of a thing. Here is a theory one from the same year, 1991, I will show. Okay, let me see how I'm doing for time. It's all right, I'm doing well. So it was basically a very famous debate that is not taught in schools or colleges. I don't even find it in advance in good textbooks. It is basically the debate between Ampere and Biot-Savart. In 1820, Ørsted discovered that when you pass a current, you basically get a magnetic field. But what is the nature of the magnetic field? How does it look? What is its value? What is its direction, etc.? That was predicted by Biot-Savart on one hand, and a different prediction was made by Ampere. So who was right? Okay. So Biot and Savart thought they were right. They devised an experiment in which a current is going like this. It comes back the other way in a V shape, and there is a bar magnet over here, a compass that rotates. Okay. Turns out that Ampere was vindicated. So in this so-called very interesting problem, which is a unification basically of electricity and magnetism, the grand unification that is happening. Okay, it was Ampere who was right, and theory problem number 2 was devoted to that. So these problems are very historical. They're also of a different kind, and I will come to it. The students who take the exam, they have 5 hours to do 3 problems in theory. They have 5 hours to do the experiment that I showed you. Okay, so on 2 different days, of course. Okay, they can't do it all in one day. And what we want from the student is the ability and not the speed, because they get 5 hours to do 3 problems. And even if they get 2.5 right, they will get a gold medal. Okay. So what, there's, for example, a chemistry type problem. It was on phase diagram, for example. There's a problem on ice. There's a problem, say, I'll read the first one, a glass container partially filled with water is connected to a vacuum pump. What changes will be observed when the pump is turned on? There are other interesting problems. Let me tell you, in the International Chemistry Olympiad that was hosted by us in Mumbai in 2001, there was a very interesting problem on a very ordinary thing called the arvind. We all know what an arvind is. We all know aloo vadi, of course. And we all know that when you take it, it can actually give you a acidity or something. So you put tamarind on it. You actually have to put tamarind on arvind. Okay. So basically you change the pH value. So one problem was on that, on calcium oxalate, of which arvind is made, and so on. Basically I have a book which describes a few of these problems, and it is both in Hindi and in Marathi. If someone who is interested, I am willing to share it. Similarly, biology has problems on evolution. Based on the data in the graph, you have to plot the correct evolutionary tree. Okay, it turns out B is correct. Then I'll let you think about it. The objective here is to be popular, to be personal, and to show you the pioneering efforts. But this is to just give you a glimpse of the kinds of problems that you have to do. Okay. And what this shows you is a typical example in which there are cubicles. There are at least 300, 400 cubicles. One student is sitting in that cubicle and doing the problem. Okay. So, and you have to be shaded because each student, for example, has to be shaded from the other people. There are proctors, of course. Am I clear? Am I quite? I mean, those are everything.
Yes, sir.
Okay, very good. So this is something that I suggested, and it was actually picked up in a very interesting way by somebody else. This is, if you're from a village close to mine, it's called a rice pounder. What is a rice pounder? There is rice grain, I mean, whole with the husk. And what a kid is doing is he's hanging onto a rope and he moves his feet. He moves his feet up and down. So this pounder goes up there and then it pounds. And you get the rice out. The husk is separated. Okay. The Vietnamese took this up. Okay. I described it to a Vietnamese. They hosted in 2008. And they had a wonderful problem for 10 marks, which I can share with you. Okay. In which they had a rice, they actually went to their own rural areas. They found how the rice pounder works. They have a water rice pounder. As the water falls, the rice pounder works and it grinds rice and makes rice. Okay. So they made an elaborate problem out of it, which is actually quite intense and difficult. Okay. So you can also do something like this. You don't have to be very historical. Here is another one which was used in the Junior Science Olympiad. This man is actually trying to climb this toddy tree or a palm tree. Okay. And look the way he is. He's got a rope here, he's got his rope tied here, and he's got his hand there. So the thing was to work out the dynamics of how he's climbing up. Okay. So we have all kinds of interesting problems in the Olympiad. And let me share some facts with you. Okay. The Olympiads are individual events. There is no official ranking of nations. That is to say, at least officially, they do not allow national jingoism. Like we are better than X. X is better than Y or something. So you get a medal. The student gets the medal. The nation doesn't get a medal. I think the Olympics is also like that, but we always start counting. Who's number one, who is number two or something. Okay. So it is 5 hours for practical, 5 hours for theory. Maths, of course, will have only theory, right? And the practical is very important. It's at least 40% of the weightage. So the theory is about 60 to 50% of the weightage. The least count, I mean, supposing I have theory, 30 marks, 3 questions, 10 marks per question. Least count is 0.1. Okay. And approximately 10% or less students get gold medals. Another 12 or 15 get silver, and the remaining some get bronze. There's another category below that called honorable mention, but these are the 3 medals like the Olympics. Okay. The paper is set by the host nation. In fact, it takes 1, 2 years. We are hosting the Asian Physics Olympiad next year. Okay, the IAPT is doing it in Erratum. But we have started making the problems right now. The problems are in progress. Okay, but it is vetted by the international board. And I will tell you what the international board is in a minute. And each country, what happens is, I'll have to tell it to you right now. Basically, the host nation makes the problem, okay? And then let me go to the next slide, I will explain. Then the host, whoever is the problem maker or whoever is one of the main persons of the theory group or the academic committee, not theory or experimental group, this is an experimental thing. He presents the problem to at least all the leaders who have come. So supposing 50 countries have come, so there will be at least 100 leaders. They will be sitting here, they will be seeing the problem 1 day in advance of the exam. So they will see it 1 day in advance, they will make comments about it, they will try to make it easy or difficult. Okay. And after that, they will translate it into their own languages, like Russian or German or Chinese or Spanish or whatever. So it has to be, that's why they have to know the problem. And the point is, since I know as a leader what the problem is going to be, physically, to be very clear, we are separated from the students who come with us. We are, of course, mentors to them, but we get separated at that point for at least a week, and we are in one hall or in one place, and they are about 10 kilometers away. Okay. So there are 5 students in physics, 2 leaders, sometimes a third observer. There are 4 students in chemistry, 2 leaders, etc. 4 in biology. Okay. So now let me come to the performance. Okay. So basically, now that you have an idea of what this is like, let me come to the performance. This is our first foray into the Science Olympiad. Was in physics, the second was in chemistry. 1998 was physics. Professor H.C. Pradhan, who was the dean at Homi Bhabha Center. Now I will talk about some of the key players in the Olympiad movement. And in the sense, I feel bad about it because I'm losing. If I give one name, I'm not saying 10 other names that I should be given. But given the short period and this constraint of a colloquium, I cannot name all of them who deserve to be named and remembered. Okay. Professor Pradhan was the dean. He was one of the key players of the Olympiad movement. Professor Natarajan was at IIT Chennai. He has been basically the chairman of the joint entrance exam. Okay. And our performance was basically, we got 1 silver, 1 bronze, and 3 honorable mentions. Interestingly, you will see, and I will just mention this, for the second problem, which was about Iceland. It was a volcanic activity under an ice cap. It was a problem on thermodynamics, mechanics, and geology. An Indian student won the Best Solution Award to that one problem, Vijay Bhatt. One other student, Saket Guha, bagged the European Society Medal for the best balance between theory and experiment. He got that award from Henry Mars, the president of the European Physical Society. Okay. So the performance was encouraging. So next year, here is a picture of the group, and Professor Pradhan over here, and Professor Natarajan. Next year, 1999. Okay. Let me show you the full thing so you can read it. Okay. We did better. From 1 silver, we had 4 silver and a bronze. Okay. And one of our students, Subrat Raju, bagged the coveted prize for the best solution to problem number 2, famous debate between Ampere and Biot-Savart. He did the problem, one part of the problem I remember, and I remember all the solutions. He did it by 3 different methods. So he got this prize. In case some of you know, Subrat Raju is a young, bright, very good theoretical physicist at the Tata Center, the International Center for Theoretical Sciences in Bangalore, that belongs to TR. Okay. So that's where he is. And there is another person I need to honor here and mention. Here it is. Here's the picture. This is Subrat Raju. Over here is a picture of Professor Arvind, the doyen of the IFPT, the one, the signatory of the Memorandum of Understanding, the coordinator of the exams at the first level with 40,000 students. In fact, they also helped conduct the chemistry, biology, and recently with the Maths Olympiad. And that is, he passed away last year, but he was an outstanding figure in the Olympiad movement. He signed the Memorandum of Understanding. Okay. And this is just to tell you, just to give you a glimpse. And since I'm telling you stories, you have to indulge me. Okay. This is again in Italy. You see Professor Dharkar. In the middle is, you cannot guess it. It is the leader of the Pakistani delegation, Abdullah Sadiq. Professor Abdullah Sadiq, I think from the University in Islamabad. And we became good friends. In fact, he was such a friendly person and such an interesting person that whenever we went out to eat or drink coffee or have pizza, he made sure that he paid. Every time I decided I would pay, or Professor Dharkar said we should be paying, he managed to somehow change the situation around and he paid. So there is a lot of goodwill also between countries in the Olympiad. It's not as intense as the Olympics. Okay. I mean, it is. Then come to next year. I'm showing you the evolution once again. We got 2 goals. Okay. And basically our position in the world was third in terms of marks. So right in the very third year, we went right to the top 3. And basically, you can see the 2 goals were by Arvind and Navneet. Arvind, of course, was taken up right away. That was in England. He was given a scholarship to go to Caltech right there. So he went to Caltech. And Navneet Loyawal joined IIT Bombay for computer science. And in 2004, when he graduated out, he became the first person Google hired in that institute or in any B.Tech place. He is the first hired person, and now he's doing very well for himself in California. So here is a pillar of the Olympiad movement, Professor Arvind Kumar. He was the director of the Homi Bhabha Center for Science Education. He signed the Memorandum of Understanding and led the Olympiad movement. Okay, so he's there. I thought this is the third person. Okay, and this is Arvind, and this is Navneet Loyawal. In 2001, I will not spend too much time. There's one person I did not mention in the previous slide, but I will tell you from 2 goals, we got 3 goals. Once again, our position was third. And some of you who are in the DAE, who are in DAE, main DAE, you would remember at least Mr. Dixit and Mr. Agarwal, Mr. Dixit, I think, was in the NPCL as one of the top ranking officers until he retired. Okay. And so is Mr. Agarwal. Whether he was in DAE, BRC, or NPCL, I don't know. But these are the kids of those people. It's like this. The father is probably, the son is better, outdid his father. Oh, I didn't show you some. I have to go back just a little bit because there's one other person I need to introduce. You have this is Professor Desai. He was a very meticulous experimentalist, a very careful and a very demanding experimentalist. He was very particular about error analysis. They used to call him the error analyst, and then they corrected it. These students were very scared of him. Okay, they started calling him terror analyst instead of error analyst. So let me shift to chemistry a little bit. You will probably recognize 2 people in this picture, 2004, the Chemistry Olympiad. This is a rather young-looking Professor Samant. And on the right-hand side, he almost looks like a boy. It is Swapan Ghosh. So they were the leaders. They were the 2 leaders who took the chemistry team. And in the middle is a girl, Priya Gupta. She was the first girl to get us a gold medal in the Olympiads, in the Science Olympiads, okay? Physics, chemistry, biology, or anything. So we are very happy, and we have to highlight her. There are other students. I mean, I have a story, by the way. As I said, if I tell you one thing, I'm sorry. I feel very sorry, and probably I will lose sleep tonight because I will not get. I have left out so many other people. For example, Sudeep Kamath. Okay, so I'm not telling you his story, which is also very interesting. He was JE rank 1. This is from the biology team, which got 1 gold and 3 silvers in 2010. The person you see here is Rekha Vartak. She kept the biology flame alive. She is one of the key persons in the biology Olympiad movement. The other 2 people are also very important, Shashi Kumar Menon and Anshuman Chakrabarty. Shashi Kumar is in Bombay, and Anshuman, of course, I think he's from Gujarat. Okay. So coming to girls, okay, a few girls, but not too many, have gotten gold medals for us. Since I'm speaking about the early period, I would like to apologize. Later on, there have been girls, but this is Priya Gupta. 2 girls in biology getting gold. There are a larger number of girls in biology and a large number of them winning gold medals for us. This is the girl in physics, Kansha Saga and Sumika Garg. They got a gold medal for us in physics. So I tell these biology, in those days I used to joke with them and said, because they didn't want to go into biology, they went into AIMS. They would get into AIMS and I said, very good. Okay, when I grow old, my life will, I will put myself in your care, so that you take care of me or something. Yeah. The Astronomy Olympiad has also done very well. This is 2006. We hosted the Astronomy Olympiad. And look at this, 5 gold, a silver, and a bronze. That is the kind of performance. I'll show you 2 others pictures, and then I will move on to something else. And let me see how I'm doing for time. That's not too bad, I think. I'm doing quite all right. Okay. This is the 2005 physics team. Not because I wanted to highlight the physics team. Here is Professor Arvind. He's a college teacher, retired now. He is the main person, the coordinator of the Asian Physics Olympiad. He's an IIPT member, and therefore I thought I should highlight him. There's a student I want to highlight, Piyush Srivastava, very unassuming, J rank 1 in that year. I'll tell you why I'm talking about it in the next slide. Okay. The next slide is the chemistry team of 2005. Okay. Once again, as I said, I've been very selective. I'm not showing you many things. Okay. This is Dr. Savita Ladge. She holds the chemistry program together at HBCS. From the ISCT side, there's an associate for chemistry teachers. There's a whole galaxy of people, including Dr. Tabu and others, who hold the chemistry flame alive. And Swapna Narvekar is another assistant, which is also she's retired now. But the person I want to highlight is this person, Himanshu Asnani, J rank 4. So Piyush Gupta, Piyush Srivastava and Himanshu Asnani. You will say, where are they? What are they doing? They are both, you'll be surprised, they are both faculty members in TIFR in the computer science. They are faculty in computer science department of Tata Institute, right here in Kolaba. Okay. Another very interesting person is this. How many stories can I tell you in 10 minutes now? Arun Paidamari. Arun Paidamari is J rank 2 in that year, by the way. He has only one functioning hand, and he has to deal with pipettes and burets and what have you. So he did this whole OCSC training camp without breaking a glassware with one hand. So here is now, after this, I think I will not show you any more results. This one and the next one. This is our performance from 2000 to 2006. You can see how our chemistry did. 2 golds, 2 silver. You can see how the physics did. Say 3 golds, 2 silver in 2001. Biology, 2000, where 1 gold, 3 silver. Every student who has gone has gotten a gold. And let me show you some additional ones now. Here is from 2007 to 12. Look at the 2008 and 2009 results of physics. 4 golds and 1 silver. That was only bettered in 2018 when we got all 5 golds. What is the budget? The budget, at least in my time, was less than 1 crore, 60 lakhs or 70 lakhs. That's it. For the whole program, not just 1 crore. What is the Olympics budget? 100 crores. And what is the output? In this period, 39 golds, 66 silvers, 22 bronze, 12 honorable mentions, because math is admittedly very tough, I tell you that. Okay, so if you don't get golds in math, it's not a bad thing. And 139 out of 130. So the strike rate is 10%. So that's it. The budget is shoestring budget. and the strike rate has been very good. The publicity by the newspapers has not been there at all. The recognition is probably missing, I would say. The Olympiad movement has gone beyond that, both for the teacher associations and for the Nodal Center, Homi Bhabha Center. Basically, there has been teacher development, school curriculum. We have put India on the national and international map, and we have even gone over to do some misconceptions research in chemistry, in physics, mathematics, biology, etc. So we have many ramifications. One important ramification is that we have gone beyond 12th standard to undergraduate. We have a program called the National Initiative on Undergraduate Science by the Homi Bhabha Center, and a program called National Training Program for Undergraduate Students, a student symposium for research by the IFP. Both, I mean, everybody has gone, and they know that there's a next level after that, and that's the undergraduate level. So for NIUS, let me just show you something. So our auxiliary work, as I said, has been NIUS, in CBSC, in NCRT, in NPSC, and also in CEBS. During the next exams in 2007, 8, 9, I think the Olympiad resource people were very instrumental at that time. Okay. And what about CBS? Let me just come first about a couple of examples of how it impinged on the Center for Excellence in Basic Sciences. I think it is stuck. Where is it stuck? Here. So here you can see the Olympiad Block in the Nodal Center. So there is the reason I'm showing it is there's a reason for showing you another picture. This is chemistry, this is biology. Okay. For 2 years, the CBS chemistry and biology experiments were done in the Olympiad and the NIUS labs. Okay. Whereas for physics, what happened is one of our key resource persons, Rajesh Khapade, and a couple of IPT members came and collaborated. It was done all over here, honestly speaking, but they did collaborate and help out. Okay. Regarding the undergraduate research, okay, here is another thing. The first paper published by an undergraduate student in CEBS was in 2011. Okay, this is Shilpi Singh. This picture is not from Bombay. I mean, she was in CBS, but this picture is in Finland, where she did a PhD from. And she published it in the European Journal of Physics. Fortunately, it was highlighted in the local newspapers. You can see the Hindustan Times reported this. 19-year-old student, this paper makes it to the European Journal of Physics. So I've come to almost to the end of my story, and I think I'm doing all right on time. So why did it succeed? I believe because there's a strong public-private partnership. The Homi Bhabha Center is right there in Mumbai, and there are these teacher associations of physics, chemistry, and biology all across India. Okay. And now there's a little bit of reflection on how we did so well, okay, and why these students were so good. Okay. So there are two views. One is a view, an American baseball coach who says winning is everything. It's not everything, it is the only that attitude people have, that I have to get it. But there's another view to which most of these students would have subscribed. It's a poet's view. Basically, it says that you do this because you enjoy doing it. I mean, these students are good, not because they're very competitive, but they're good because they enjoyed that subject, whether it was chemistry or biology or whatever. Okay. Nor fame nor honor made me fight, nor public men nor cheering clouds. A lonely impulse of delight drove to the tumult in the skies. The moral of the short story is government institutions are effective, some of them at least. The Homi Bhabha Center for Science Education. Voluntary science bodies collaborate effectively. They're not always there to criticize and grab newspaper headlines. And we have perhaps the world's largest manpower in science and occupy a very high position in physics, chemistry, and biology. at the school level. Thank you very much.